Hello, everyone. My name is Alessandro Perego, and I'm a PhD candidate in polymer engineering at the University of Akron in Ohio. I currently work for Dr. Fardin Habas, and today I'm going to talk about how we can use a new computational technique to study the rheology of covalent adaptive network, and specifically of V-tumors. We live in a world that is in which we are surrounded by plastic and plastic products. In fact, as we can see in the last 60 years, the plastic production has spiked exponentially. It is estimated around 7.82 billion tons of plastic are produced globally. Now, from a polymer engineering point of view, this is great for jobs, but from an environmental standpoint, this is not as good. In fact, plastics is, as we all know, is extremely difficult to recycle and reuse. And even if the numbers are going up year by year, as of 2017, only 19% of the plastic produced globally was successfully recycled. Now, recycling plastic has a lot to do with legislations and economical factor. However, there are some drawbacks still from a scientific and technological standpoint. What do I mean by that? Well, to understand that, we need to understand how polymers are usually classified, which is mainly in two categories, thermoplastic and thermoset materials. So thermoplastic polymers are polymers in which the polymer chains are simply entangled with one another, which allow them to diffuse, to self-diffuse with each other, and also upon heating, they can be melted and softened, which makes them extremely hard to reprocess and reuse. However, they show, because of this tendency to melt at high temperature, they show really poor temperature and mechanical performance, as well as poor solvent resistance. To increase the mechanical properties of thermoplastic material, we can cross-link the polymer chains and allow them to not diffuse within themselves anymore. And so the polymer chains, now that are chemically cross-linked with one another, they cannot allow the network to not be melted or softened by heating, which will allow us to achieve excellent temperature and mechanical performance. But the main drawback is now they're really difficult to reprocess and recycle because they will not dissolve with solvent and they will not melt with heat. And thermoset, just to give you a perspective, represent 30% of the total plastic production. In fact, if you think about epoxy resins or even vulcanized rubber, all of these we can treat them as thermoset materials, and they're all around us and very, very difficult to reuse and recycle. So, is there a way to get the best from both worlds? Meaning, can we get the mechanical performance of thermoset while keeping the ability to be melted and reprocessed of thermoplastics? Well, it turns out that somehow we can. And the way to achieve this is to introduce then what are called dynamic cross-linkers in the network. And what I mean by dynamic is that once the network is cross-linked, upon some external stimuli such as heat or sound or UV light, this cross-linker become dynamic in nature, allow to be flow like thermoplastic, allow the network to flow like a thermoplastic material. And this kind of network, like this thermoset with dynamic cross-linker inside, are called covalent adaptive networks. And these ways, by introducing this, we can now think about recycling, reprocessing thermoset, self-healing material, shape memory, and even, why not, 3D printing thermoset material, which is, as of now, really unheard of. There are a lot of chemistry that have been proposed to achieve these covalent adaptive networks, with their pros and their cons. But a really promising one, which was proposed in 2011, use a trans-esterification reaction to achieve something really interesting. And let me explain this. So let's see we have our polymer chains in blue and the cross-linker in red. As we hit this covalent adaptive network, the cross-linker change position, so there is some dynamic nature in it. However, the number of cross-linker itself remain constant throughout all the process. And what does that mean? Is that the fixed cross-link density of the network stays constant. And because of that, we can still have the polymer can be reshaped upon heating due to the dynamic of this bond exchange mechanism. But since the number of bonds remain constant, the polymer does not dissolve in solvents and can keep the same mechanical properties that we're looking for in a thermoset network. These materials are known as Witchmers, and they show really interesting rheology. To understand that, let's look what a thermoplastic volume versus temperature plot will look like usually. So at high temperature, we're in a rubbery regime or viscoelastic liquid in which the thermoplastic flows. As we cool down the system, the ability to flow gets lower and lower, and then we reach what is characteristic of the network, which is the glass transition temperature, below which the polymer is in a glassy state or out of equilibrium. If you look at the viscosity by doing the same process, by cooling down the system, we see that the viscosity abruptly increases as we approach Tg, following what is called the Williams-Landau-Sperry equation, or most commonly known as WLF equation. Now, for a Witchmer, at really high temperature, we are in a viscoelastic liquid, so the dynamic of the bond exchange will allow us to have the network to flow, even if it's a thermoset material. But as we cool it down, we reach something specific of Witchmer, which is called the topology freezing temperature, or TV, below which the network will behave like a viscoelastic solid, so we will have the properties of the thermoset that we're looking for. And then, as we cool down again further, we reach a classic ground transition temperature typical of polymer networks and both thermoset and thermoplastic. The interesting feature of these materials is their viscosity behavior, however. As we cool down, the viscosity increases as expected, but not as abruptly as the WLF model, but more like an Arrhenius-like behavior. And since this behavior is seen in organic material, such as silica, that's why the name Witchmer was chosen to describe these polymer networks. Another interesting feature is when we study the elastic models of these materials, we can really see the difference between the thermoset and the Witchmer. As at high frequency, we are in a glassy regime, which we will enter a transition regime by lowering the frequency. And then in normal thermoset cross-link material, we reach what is called the rubbery plateau, or which is also sometimes called the infinite rubbery plateau, because this plateau will not go down. However, for the Witchmer, we enter a terminal liquid regime, which again is one of the hallmark of these materials, which allow us to reprocess them and melt them. So due to the novelty, there is still a lot of unanswered questions, especially on a molecular level, about the dynamic of this bond exchange inside the network. So our objectives is can we use molecular dynamic simulations to answer these three questions? The first one is can we estimate the topologic freezing temperature from volumetric and rheological data? Now, this is still a debate in the experimental world, as there is not experimental study done yet that we're able to estimate the TV from volumetric experiments. So can we do that using simulations? The second objective is what is the impact of the lifetime of the exchangeable bonds on the rheology and the dynamics of the Witchmers? And lastly, can conventional rheological methods such as the time-temperature superposition principle create the full spectrum of the rheology of Witchmers in simulations? So the method that we proposed, which was recently published in the Macromolecules a couple of months ago, is by using a coarse-grained molecular dynamic model based on the bit spring model, where the bonded interactions are based on the Finney potential here. So how does it look like? So here we have these polymer beads, which are the blue one, which we decided to go for a 10 mer, so 10 beads, mixed together with a tetrafunctional cross-linker, the orange one in this picture. And then by using simulator annealing, we cross-link the network. And once the network was cross-linked, we use a Monte Carlo step to do the exchange reaction. And let me further explain this. So here is our tenomer with the tetrafunctional cross-linker, which are bonded. And then upon a Monte Carlo step, the bond exchange happens. And so how does this work? So at every molecular dynamic step, we perform a Monte Carlo step in which the energy of a single exchange gets computed using this formula. And then if the energy of the proposed move is less than the previous configuration, then the exchange is accepted right away. Otherwise, if it's greater, it's going to be accepted with a probability p based on the Metropolis algorithm. And I invite you to read the paper for more details about the algorithm. Furthermore, we can also calculate in every MD step the number of successful bond exchange in the whole system and divided by the number of trials of bond exchange, and we call this PMC. And we can plot this as a function of temperature, and we can see that as temperature rise, the probability increase, and it also fit an Arrhenius-like behavior. So now that our model is constructed, we can do some volumetric study under equilibrium condition. And so we put our system under constant pressure and temperature, and then cool it down to see how the specific volume will change as a function of temperature for both a AiChE, which is the blue line, and the thermoset material, which is the red line. And so as we cool down the system, we reach the classic transition temperature, the gas transition temperature for both AiChE and thermoset, which it should be around the same, because at that temperature there is not any bond exchange happening at our time scale. And so we calculate that our TG is around 0.45, which is less than the TG, which is higher than the TG for the uncross-linked polymers, which is what we expected. However, we don't see a clear deviation from the thermoset to calculate the topological physics temperature. So in order to do that, we can analyze the coefficient of thermal expansion alpha and plot it against the temperature as well. And here there is a more clear divergence that happens as we increase the temperature. And we propose that this divergence, the beginning of this divergence, is indeed the topological freeze temperature TV. And we estimate it to be around 0.87. Other than the volumetric study, we can do some rheological study under non-equilibrium condition. And the way this is done is really similar to what you would do in a normal rheometer in your lab. So we can do some small amplitude oscillatory stress, which means that we can prescribe some strain to our system, so the blue line, and then we can measure the stress response, the oscillatory stress response of the system. Now we can fit this line and calculate our G prime and G double prime, so our elastic and loss modulus for the system. And once we do that, we can see what the difference is between the thermoset material and a AiChE. So for a thermoset, you can see that at low temperature, we are in the glassy regime, and then there is a transition zone happening, and then we can see that at high temperature, all the curve collapse at low frequency, indicating this rubbery plateau that we were expecting. For the Vietnam, however, the story is different. So we see that the glacial regime still happen at low temperature. We see a transition zone. But as we increase and increase the temperature, the rubbery plateau is not there and is what we were expected. The question now is, can we extend the simulation timescale and pull out the whole rheological behavior of both the thermoset and the Vietnam? And it or not, we can. So we can apply the principle of time temperature superposition due to the self-similarity of the curves, and we can use some vertical and horizontal shift factor, and by choosing a reference temperature, which in our case was 0.6, we can collapse all this curve into a master curves, and from the thermoset we can clearly see what we will expect. So the glacial regime, the transition regime, and the rubbery plateau. However, for the Vietnam, we, as I say, we can still see the glacier and the transition regime, but after a small rubbery plateau, this shoulder, the liquid regime happen and is indeed what we would expect for these dynamic networks. Now, the rubbery plateau is not as extended as we would like to, but the reason is because at this reference temperature, the time scale of the exchangeable bonds coincide with the time scale of the external deformation, meaning that this rubber plateau turned out to be more like a shoulder-like transition. However, the change in slope clearly indicate a transition region from a rubbery to a viscoelastic liquid regime. Lastly, we can plot the shift factor obtained from collapsing buster curves as a function of temperature. And indeed, we see the two different behavior that we will expect. So at high temperature, we see a divergence of shift factor in which the shift factor for the Vietnam follow an Arrhenius-like behavior, where the shift factor for the thermoset for a WLF behavior. But as we cool down, the shift factor collapses to be the same, as the dynamic is so slow that the thermoset and Vietnam behave the same way. And so they both follow a WLF fit. The last thing that we want to confirm was the behavior of the zero shear viscosity at temperature greater than TV, so 0.87 for our case. And by plotting the zero shear viscosity as a function of inverse temperature, we can clearly see the Arrhenius-like behavior typical of Vietnamers, which indeed confirm the accuracy of our model. So in conclusion, we proposed a hybrid molecular dynamic Monte Carlo technique that can successfully mimic the bond exchange reaction in Vietnamer. The model with the head of the time temperature superposition principle captured the rheology at low, at high end regimes. The topologic freezing temperature can be determined from both volumetric and rheological data, as we've seen. And then the objective that we have now that we're working on is try to extend this rubbery plateau for the Vietnamer, and which will allow us to gain a better picture of the rheological data. I would like to acknowledge for this work, I would like to acknowledge my advisor, Dr. Ferdinand Habas, for his guidance during this whole project. My PhD colleague, Dario Lazarenko, for her help as well in analyzing and processing some data. And then I would like to thank Dr. Michel Claude from SPSC and CNRS in Paris, which acted as a project consultant for us during the whole process. And with that, I will be available during the conference to answer any questions. But thank you very much for tuning in.